Alright, so we're going to continue on from where we left off in the last video and start moving in the direction towards using intervals. But just as a reminder, let's do another example using that z interval that we were dealing with in the previous video. So let's do example 3 here. It says a website gave a point estimate for the average height of NBA players as 79 inches last year. If they sampled 60 players and the population standard deviation was 3, find the confidence interval for the average height of NBA players with 95% confidence, and then interpret our results. So what we're trying to do is find a confidence interval. If you remember how we did that last time, using our calculator, we went to the z interval on our calculator. Now, z interval is in the stats menu over in the tests section. Now be careful, there's a z test. We don't want that one. We want the z interval, which is the number 7. Now the reason we are using the z interval is because we know the population standard deviation. So when we know the population standard deviation, we use the z interval. Let me scroll down to the guided notes where we left off last time. Whoops. And deal with the NBA height. So again, what we're doing is we're using the z interval since we know the population standard deviation. All right, so we're looking for averages. We know our population standard deviation. Again, the z interval, we go into stat, tests, number 7, z interval, and we're going to inputs our inputs from this one are going to be the statistics that I'm given up in the problem. The first input that I need to plug in is my population standard deviation of 3 inches. Then I need to plug in the average of the sample, which was 79 inches. I then plug in the sample size, which was 60 players that they sampled. And we want to use a 95% confidence level, so we're going to use a C level of 95. Now, the interval that I got was 78.241 to 79.759. And what that means, or how we would interpret that, we would say we are 95% confident that the average height of all NBA players is between 78.241 inches and 79.759 inches. So that's our interpretation there. We're 95% confident the average height for all NBA players is between 78.241 and 79.759. Now here's the deal. 79 inches, by the way, 79 inches is 6'7", so that's very tall, obviously. We could ask a question like this. Would it be unusual if the average height of the teams playing in the NBA Finals was 6'3", or in other words, 75 inches? That would be unusual. All right. Again, we're saying that the average for the NBA players should be between 78.241 and 79.759. So if we had a big group of them, like, I don't know, the 20 playing in the NBA Finals or so, it would be very unusual for their average to be 6'3". Now, on the other hand, would it be unusual if we found one NBA player that was 6'3"? Of course not. No. We would expect people individually to be outside of that interval. So again, when we're talking about big groups, we're talking about averages of the group. So the average of the group, it would be unusual if a large group of NBA players was under 6'3", but it's not unusual for a few NBA players to be under 6'3". Hopefully that makes sense. So if you pick a random group of NBA players, their average should be close to that 79, or at least within this range. But obviously there's going to be some individually who are outside of that range. So there you go. Again, to emphasize, we use the population standard deviation. So, or let me say it, reverse that. We had the population standard deviation. So since we knew the population standard deviation, we used the z-interval. Now what happens if we know the sample standard deviation? Well, if you don't know the population standard deviation, then you're going to have to use the sample standard deviation as an approximate for your standard deviation of the population. So in other words, all we're going to do is we're going to switch out using population standard deviation to using sample standard deviation in that formula. Now, because sample standard deviation is an approximate for the population standard deviation, we're going to use something called a t-interval. And instead of having z values out front, we have t values. Okay? This is known as the t-interval, or also known as the student's t-interval. Now, student does not refer to people who are taking classes. Student was actually the last name of a mathematician that this was named after. So a student's t-interval, if you ever see that terminology, this is what it is. Notice how similar it looks to the z-interval. It's basically the same thing, except we swap out the population standard deviation for a sample standard deviation. And since we did that, we go from z values to t values. Now, you might ask, well, what are these t values coming from? The z values that we used in the z-interval came from the central limit theorem. Well, what the t values are they're basically a stretched out version of the normal distribution. Let me say it this way. These t values come from the same logic, from the same sort of set of ideas, but instead of coming from a normal distribution, they come from a stretched out version of the normal distribution in the central limit theorem. Hopefully that makes sense. So z values came out of the normal distribution from the central limit theorem. T values are basically just a stretched out version of the normal distribution. And it turns out how far you stretch it out, how far you manipulate it, depends on how big your sample size is. All right? So I'm not going to go through what the t-interval is. If you wanted to Google that, you can Google t-distribution and kind of get some pictures of what it is. It looks just like a normal curve, but again, stretched out from what you would have seen in the central limit theorem. So let's do an example here. This says, according to some internet post, a sample of 15 college heavyweight wrestlers had an average weight of 255.88 pounds and a sample standard deviation of 19.29 pounds. Find the 90% confidence interval of the true mean weight of all college heavyweight wrestlers. So here, the big change is instead of having a population standard deviation, I have a sample standard deviation. So because I have a sample standard deviation, I am going to have to use the t-interval. Now you can guess, and you'd be right, that as far as use of the t-interval versus use of the z-interval, there's not a whole lot of difference. So you would go into the same menu in order, so if you're trying to use the t-interval, you go into the same menu, go stats, tests, where the z-interval was number 7, the t-interval is simply number 8. Okay, the inputs aren't changed a whole lot. The only really change on the inputs, again, we're using statistics here. The only change is the order. First on the t-interval is our average. So our average weight was 255.88. So I'm going to type that into my calculator. My standard deviation was 19.29. That is sample standard deviation, again denoted by S when you use the t-interval. My sample size is 15. And in this case, the confidence level is 90. So once again, just really quickly, to get to the t-interval, stats, and then into the tests menu, and then number 8 is the t-interval. So I'll write that down just so we don't forget. So I type in all of my statistics and I calculate, and it might take just a little, I don't know, a fraction of a second longer than to compute the z-interval because those t values actually depend on your sample size. So they do have to, your calculator does have to do another step to get this. But just like the z-interval, it pops out as 247.11 to 264.65. And we're going to interpret this the exact same way. We are 90% confident that the average weight of all college heavyweight wrestlers is somewhere between, or just between, 247.11 pounds and 264.65 pounds. Now, one little aside here, notice that I am leaving the decimal point on, and I always use whatever the calculator gives me. So if the calculator rounded these to 2 decimal places, I would have just used 2 decimal places here. In the previous example, the calculator rounded to 3 decimal places, so I just used 3 decimal places there. So I kind of, on the test or whatever, I would round those. I wouldn't necessarily round those things. I just leave them to wherever the calculator rounds them to. On the homework, you might be asked to round to 2 decimal places, but for the test, I would just leave these things as they are. So again, we are 90% confident that the average weight of all college heavyweight wrestlers is between 247 and 264. Now, if a coach claimed that the average weight of heavyweight wrestlers was 280 pounds, that would not be believable. All right? We expect that the average weight should be somewhere between 247 and 264. So that would not be believable if somebody claimed that the average weight was 280. However, if the coach claimed that his wrestler weighed 280, that would be believable. All right, yes, obviously individuals fall outside of those bounds. In fact, probably most individuals might fall outside of those bounds. But the average of the group should be in between there. Let's look at another example. And this time, we're going to use some data instead of using statistics. So this says that the number of deaths by all rifles per year from 2012 to 2016 is given below. So treating these data as a random sample, construct a 98% confidence interval of the average number of deaths by rifle per year. So these data show deaths by rifles. All right, now this is all rifles, so this is accidental shootings, uh, shootings on purpose, big gunman scenarios, whatever they're called, lone gunman scenarios, all deaths by all rifles in those years. Okay, so here's how we would do this. First off, I need to contrast this with the previous example. Notice in the previous example, we were given the average. We were given the sample standard deviation. We were given the sample size. In this, I'm just given the sample directly. So what I can do is I can have my calculator actually deal with this sample directly. So we will just put the rifle deaths data into list 1. So put the rifle deaths data into list 1. Again, if you forget how to do that from previous chapters, stat, edit, and then you're in your list menu. So input the rifle deaths data into list 1. And now we're set. Now, I want you to note that I am not given a population standard deviation. But we are talking again about the average. So we're talking about the average. I don't have a population standard deviation. However, when I compute these things, I would get a sample standard deviation if I wanted to. You could compute that by yourself. So I don't have the population standard deviation, and therefore I need to use that t interval. So once again, stats, tests, t interval is number 8. And here's where we come up. Uh-oh. So, sorry about that. T interval is what I'm going to use. My input, in this case, needs to be data. So we need to scroll over, make sure our input is on data. And what you're going to see is, like a lot of times when we use data, is a list and a frequency. Now, the list that we're going to use is L1. Again, this is second and then the number 1. The frequency that we're going to use, well, we're just going to put in the number 1 because everything on our list, when I type that in, I typed it in and I'm assuming each one of these numbers stands for a single year. In other words, we don't have a frequency distribution. If you had a frequency distribution, you do list L1, frequency list L2. We don't have a frequency distribution, so that's how we're going to use that. And then the confidence level obviously is 98 because we're looking for a 98% confidence level. I won't even write that down. When I go to calculate this, I get 214.73 up to 374.47. And the interpretation would be we are 98% confident that the average number of deaths by rifle per year for all years is between 214.73 and 374.47. So that's a little bit weird, but average number of deaths by rifle, maybe I should just skip this part per year, for all years is between 214 and 374. Now, notice I did not round that to the nearest whole number because while you can't get 214.73 deaths, you can get the average to be 214.73. So an average obviously doesn't have to be a whole number, even though number of deaths does have to be a whole number. So there you go. There you go. And again, it would be kind of unusual if there was like a 10-year span in which the 10 years fell outside of there, but it's probably fairly common to have a single year be lower than 214.73 or higher than 374.47. So here's what I'd like you to do. I'd like you to take this problem and try to do it yourself. Decide whether you have to use a t or a z interval, and then go ahead and compute the confidence interval for this problem. Push pause on the video, and then I'll come back in about 5 seconds. All right, so hopefully you went and did that. We can see this is talking about hurricanes. Now, which interval we pick, well, in this case, we're going to use a t interval. Okay, and the reason is I have a sample standard deviation. All right, so we're going to use a t interval, and we're going to use the stats version. So again, stats test number 8. You can use statistics. My average, well, the average number of hurricanes per year says is 6.3. The sample standard deviation is 2.9. My N is 51 because we did this over the 51 years. That's my random sample. And we wanted a 99% confidence level. So when we put all that together, we calculate, and we get a t-interval, which is 5.2126 up to 7.3874. Okay, so my interpretation statement is we are 99% confident that the average number of hurricanes for all years is between those numbers. All right, so that's it. That's it. Again, and let me just remind you, there's probably a few years that, maybe a lot of years that you get less than 5. There might be a lot of years where you get 8 or more. But those things, what we're saying is not that we are not saying 99% of years fall in there. What we are saying is that when you take a big group of years and average them up, they'll fall between those two numbers. I want you to try one more on your own. Read this one and then do the problem. Pause the video and I'll come back in about 5 seconds. All right, so we're looking at the women's outdoor track and field championship winners, and we're looking at their average with a sample, no, it doesn't say sample or population, doesn't. So we say during the 18 years from 2000 to 2007, the women's outdoor track and field team scored an average of that many with a standard deviation of 9.06. Treating those 18 years as a random sample, find a 96% confidence interval for the average number of points scored by those champions. Now, does this standard deviation, it doesn't have a signifier of sample or population, but in the context of the problem, I hope that you can understand that the standard deviation is referring to just those 18 years. So it must be referring to a sample standard deviation. And so you're going to use a t-interval. So we use the t-interval against stats. Then we plug in the average of 64.06, the sample standard deviation of 9.06. We know we're doing this for a sample of size 18, and we want 96% confidence. So what I found as my confidence interval, should have done that earlier. I found that in the t-interval came out to be 59.311 up to 68.809. And what's that mean? That means we are 96% confident that the average points scored for the women's outdoor track and field championships. For all years is between those numbers. Again, what this is saying is that the average for all years is between those numbers. But again, there's going to be many years where it falls outside of that. Maybe you get less than, maybe you get more than. So hopefully that makes sense. Again, the determination between Z and T is, do we have a sample standard deviation or do we have a population standard deviation? A population standard deviation, we'd use Z. A sample standard deviation, we use T. Now, both of those are for finding averages. So confidence intervals about averages, I should say. It turns out that you can also deal with things that are not just the averages. So you can find confidence intervals of things that aren't the average. They're going to be very similar features. They're going to have similar features to the Z interval and T interval, but we're going to use different formulas. And what we're going to focus on in this class are the confidence intervals for proportions. So here is what the confidence interval for a proportion looks like. Now, what this is saying that if you take a sample and find a proportion on a sample, the proportion of the population is going to be somewhere in between the sample proportion minus a z value times the square root of p hat q hat over square root of n. And then obviously p hat plus z alpha over 2 square root p hat q hat over square root of n. All right. Now, let me just point out this first off. We're using z values again. So that means that somewhere I'm using a normal curve. And the way that the proportion interval is connected to the normal curve is through that binomial distribution that we looked at in chapter 4. So if you remember the binomial distribution, it turns out if you would have drawn a histogram of the binomial distribution, as long as you have a fairly big value for n and your probability is not ultra low, as long as the bigger the n values, the more that binomial distribution is going to be normal shaped. So the binomial distribution is going to be normal shaped, so we can use that normal curve, we can use z values. So that's why we're seeing those z values. Now notice what this is. This looks kind of like standard deviation divided by square root of n. It turns out we just replace the standard deviation with a square root of p hat q hat. And again, the p hat is the proportion of the sample who were successes, and q hat is the proportion of the sample that was failures. Once again, we're going to use our calculator to sort of simplify this, but you should be able to recognize that formula if given to you on a test. All right? Now remember, we're using p hat and q hat, and I said p hat is the sample proportion of successes. So it's the probability of success on the sample. Q hat is sample proportion of failures. So think about what that means in binomial notation. Binomial notation meant, well, we had x is the number of successes, n is the size of your sample. So basically, the binomial notation says that p hat has to be the number of successes divided by our sample size. This will probably make most sense by just doing a problem. So it turns out that a Pew Research poll, I believe this was done in 2011, found that 871 out of 1,502 US adults said that the US must be at the forefront of future space exploration. In other words, they agreed with that statement when it was read to them. We're going to find the true proportion of adults who think that way. And we're going to find a 92% confidence interval for that. So here's what we do. We go once again to our calculator. And maybe before I start, let me just say something real quick. So in this case, the sample of the proportion of success was 871 out of 1502. All right. So the proportion of success would have been 0.5799. All right, rounded to 4 decimal places. So most of this would have been reported as like 57.99% of people think the US must lead, or 58% of people think the US should lead in future space exploration. This is the point estimate of that problem. This is the single proportion that you would use while doing this problem. Okay, so if it asks you for the point estimate of a proportion, that's what it is. Now, we don't want a point estimate because we understand confidence intervals. And when you're dealing with proportions, you're always going to use what's called a 1 prop z interval. Now, why is it a 1 prop z interval? Because we're dealing with one proportion and we're allowed to use z values because that binomial distribution is normally shaped. Again, if we're taking large enough samples, okay, which we are. I mean, we're taking 1,502 adults. That's a pretty big sample. Okay, I'd only have to worry if there's a special technique. Basically, you just take n times p, or n times p hat, and make sure that it's over 5. So 1502 times 58%, that's well over 5. And then also 1502 times q hat has to be well over 5 as well, which in this case it is. Don't worry about that too much. I'm not going to give you a problem where we can't use the normal curve as a stand-in for the binomial distribution. So that's a little bit of the side. So we want to go to 1 prob z interval. Now 1 prob z interval, it's in the exact same place you would think it is. Stats, tests, the 1 prop z interval is all the way down. On my calculator, it's on letter A. Now again, be careful. This is not the 1 prop z test. This is the 1 prop z interval. Okay, be very careful about that. Letter A on my calculator. The inputs are going to be x and n. Now, what did we say X is? X is the number of successes. So our number of successes is 871. N is the sample size. We sampled 1502. And then the confidence level, well, in this case, it says to do a 92% confidence interval. And so that's what we did. 92% confidence interval. And so with a 92% confidence interval, I get, let me actually just write it here, 0.5576 up to 0.60219. So what's that mean? Let's interpret it. Basically, that means we are 92% confident that the proportion of all U.S. adults who think the U.S. should be at the forefront of space exploration is between those two numbers, 0.5576 and 0.60219. Again, on the test, just round to whatever your calculator gives you. On the Moodle homework, be careful. You might have to round to 4 decimal places or something like that. Now, I want to point out a couple of things, how this changed from previous problems. In our previous problems, we were dealing with averages. So we'd always say we're 92% confident that the average of something. Now, notice we're saying we're 92% confident that the proportion. Since I'm using proportions, make sure you use the word proportion, right? And don't do the weird thing where you say average proportion, because that doesn't make any sense. So just use the word proportion when we're dealing with proportion. Just use the word average when we're dealing with average. And the wording, again, is not that far off. One thing I do want to mention, something that people will often screw up on, is they'll write 0.5576%. They'll try to write or try to do a percentage versus a decimal. 0.5576% is less than 1%. We want either 0.5576 as the proportion, or you could write 55.76 as the percentage. I'm always going to use decimal points on all my problems because I think those are a little bit easier and those match up with your calculator better. So let's take a look at the next poll that was done. I believe this one was this one was done by Rasmussen. I want you to go ahead and try to do this problem and then interpret what that means. All right, hopefully you did that. Again, we're going to go to the one prop z interval. This time, when we go there, my x value is going to be 512, and my n is going to be 1,000. So 512 out of 1,000 likely voters. The confidence level is 95% or 0.95, and we calculate. So what this would say, let's do another, I don't want to do that. or what we would say about this. I'll just go right to my statement. We would say we are 95% confident that the proportion of all likely voters who feel that the Democratic Party is the party of, quote, identity politics and victimology is between 0.48102 and 0.54298. All right, so there you go. We are 95% confident that the portion of all likely voters who feel that the Democratic Party is the party of identity politics and victimology is between 0.48102 and 0.54298. I think they want me to capitalize that P. There we go. All right. So there it is. Again, finding the confidence intervals. Now again, what I'm trying to use here is stuff we talked about in chapter 1. It is okay to look at polls about people's feelings of the Democratic Party or the Republican Party or what have you. It's perfectly okay to look at those polls and see what people are thinking. Okay, this is not an anti-Democratic Party question or a pro-Democratic Party question. Again, if you were in the Democratic Party or if you were not in the Democratic Party, either way, you'd probably want to feel, or probably want to get a feel of what people think about that group. All right, so there we go. Now, one more problem, and I want to throw a little bit of a curveball at you. So far, these previous two problems, examples 8 and 9, have given you the number of successes and the total number of people polled. But what if we gave a percentage of the sample? So we gave you the p hat and the number of people polled. I want you to push pause on the video and think through what you would plug in into your calculator and what the confidence interval would be, and then how to interpret this. So push pause on the calculator. 5 seconds, I'll come right back. All right, so here's what we're going to do. We read the question about tax breaks for NFL teams, and what we see is that 67% of people said they don't like them. All right, so they oppose tax breaks for the NFL. Now, obviously, we're talking about proportions here. I want to underline that. I apologize there. So we're dealing with one prop z interval as again. We know that that's at our calculator. The inputs are the number of successes and my sample size. That would be a lowercase n. There we go. Now, the sample size is pretty obvious. It says in a sample of 1,000 US adults. The X value is a little less obvious. It says 67% of people said they opposed tax breaks for NFL teams. Now, if 67% of 1,000 people opposed tax breaks for NFL teams, well, we could just find the X by taking 67% multiplied times 1,000. So 67% of 1,000 is 670. By the way, your calculator will not be able to handle decimals. So if it was like 67% of 1,001, and it came out to 670.67, you'd have to round that to whatever the nearest whole number is. So in this case, it doesn't. In this case, it comes out as a nice whole number. And so we go for our one prop z interval. 670 is the x value. The n value is 1,000. The confidence level, we wanted a 97% confidence level. That's what the problem asked me to do. And so I would just hit enter. And you should get a p hat there displayed as 0.67. That's your point estimate. And the way we would interpret this, we'd say we are 97% confident that the proportion of U.S. adults who oppose tax breaks for NFL teams is between, and I got 0.63773 and 0.70227. All right. So there we go. The proportion of U.S. adults who oppose tax breaks for NFL teams is somewhere between about 63.77% and about 70.23%. Now, the last thing I wanted to mention on all of this stuff was the following. So when you're calculating confidence intervals, you are going to have to be able to read a problem and determine whether we're asking about proportions or we're asking about averages. When you're asking about proportions, we're going to use that one prop z interval feature. In other words, we're going to use the proportion interval. Now, when I'm asking about averages, I have another decision to make. And that decision is, do you use the t because you know the sample standard deviation, or do you use the z interval because you know the population standard deviation? Okay. I will say this, in real life, when you're talking about averages, you almost never have the population standard deviation. Usually, you just have a sample standard deviation to go off of in real life. So in real life, you tend to use the t interval way more than the z interval. But again, a lot of times statistics classes aren't real reflective of real life. So maybe the examples in the book, or maybe the examples like on a test or something, a lot of them will have population standard deviations given. So this is it for the computing intervals and interpreting side of things of Chapter 8. In the next section, what we're going to do is we're going to utilize these formulas, namely the z-interval and the one prop z-interval, in order to come up with sample sizes. So we'll see you in the next video.